Okay, so we're going to continue with our lecture on external energy, the second part. So we just finished talking about last time the Coriolis effect. And one of the results of the Coriolis effect is whenever air is moving from high pressure into low pressure, Coriolis effect deflects it so that it, in the northern hemisphere, it spins counterclockwise as it moves in. And whenever high air is descending, so this would be low pressure, there's low, so air is moving from high to low. Whenever air is descending, so this is high pressure, and it's moving away to high, it spins clockwise. But this is why cyclones, or any sort of storm, a cyclone is a rotating air mass. So that's why cyclones rotate counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. That's because of the Coriolis effect. So, and the Coriolis effect is also responsible for the direction of our prevailing winds. So here we said, the most solar energy per unit area is absorbed at low latitudes. All right, so this is the warmest because of the more direct angle of the sun with the surface of the earth. So the very warm surface heats up the air, and that warm air rises. Then it begins to move to higher latitude at altitude, and then it sinks. And when it sinks, some of the air moves back down towards the equator. I'll just focus on the northern hemisphere. It moves back down towards the equator. As it's traveling south, in case northern hemisphere, its path, instead of traveling due south, is deflected to the right. It's deflected to the right. And so in this band between 0 and 30 degrees north and 0 to 30 degrees south, the air travels, prevailing wind it's moving from the east to the west. Now we name winds based upon where they're coming from because they're bringing the properties of the surface where they were with them. So a wind blowing from the east is called an easterly wind, right? A wind blowing from the north is called a northerly wind. So here, if we have northerly winds, they're going to be cooler because they're coming from the north where it's cooler. If we have southerly winds, they're going to be warmer because they're coming from the south where it's warmer. But we call these the easterlies, these winds. Another name for them is the trade winds. Okay. Now, some of this air, instead of returning back towards the equator, it moves towards the poles. And as it moves north, its path is deflected to the right in the northern hemisphere. And so the wind is blowing from west to east. And so these are called the westerlies, the prevailing westerlies. And so our winds are westerly winds. So that's why if you're ever, watching the weather, the person on the TV is always referring to, when they look at the map, all the activity that's to the west of us. Never referring to what's over the Atlantic. It's always what's over here, because the westerlies blow the weather from west to east. So my parents say they live in western Pennsylvania. If I don't know what the weather's going to be like tomorrow, I just call them and say, hey, what's your weather like today? Because usually it takes about a day for whatever's there to move over here, because they're almost due west of us. All right. And so that's how we get the trade winds, or the easterlies, in these low latitudes. And mid latitudes, we get the westerlies. All right, so we have the rising air. So, I forgot to mention, these trade winds, they flow, they converge, they collide, and whenever they collide, they rise. They rise up into the air. And where they collide, that's called the ITCZ. It's called the ITCZ because it's known as the Intertropical Convergence Zone. Intertropical Convergence Zone. There it is written out right here, the Intertropical Convergence Zone, ITCZ. So that's where these easterly winds collide, and then they rise. Some of the air falls, and it returns as an easterly wind or trade wind. As this air falls, some of it moves to the north as a westerly wind. And these are cells, convection cells, so the air is rotating. So this is a Ferrel cell. This is a Hadley cell. and then this is a polar cell. So there's 3 convection cells in each hemisphere, northern and southern hemisphere. All right. And so the middle in high latitude, so Hadley cells, that's this tropical convection cell. They create bands of high pressure at about 30 degrees north and 30 degrees south. Why high pressure? Because that's where the air is descending. Remember, descending air creates high pressure. So that's high pressure is good weather. So usually good weather there. Air flows away from the high pressure zones. Cold air flows over land from the poles. They collide at a polar front around 60 north and 60 south. So if I can maybe erase some of this. So this air, as it rises, as it descends, it moves this way. Some of this air moves this way and they collide and they form this polar front. This air is colliding. This air moving this way and this air moving this way, about 60 degrees north. And so the Halley cell, the ferrocell and polar cells, and the ITCZ and the polar front, those are the main features of the circulation of the atmosphere on Earth. And these are basic global wind patterns, but they are modified by the locations of continents, mountain ranges, and they vary with the seasons and Coriolis effect. But so here you can see, in essence, how this polar front develops. So you have this warm air, or this is not a polar front, this is just a front. Warm air moves up where this cool, dry air moves down. And air that's different temperature and humidity has a different density, and they don't like to mix. So it forms a boundary, which is called a front. And I'm sure you heard of a front, like a warm front or a cold front. Right, and that's where storms develop, at least at higher latitude. They form along fronts. And so in North America, we have cold, dry air from the north, which moves south, and we have warm, moist air from the south that moves north. And then they collide, they form fronts, which storms form along, and then the westerly winds blow those storms from west to east across the country. That's basically where a lot of our weather comes from. So fronts are 2 air masses that have different densities. So an air mass can have a density of air depends on its temperature and its humidity. The warmer the air is, the less dense it is. And actually, counterintuitively, the more humid the air is, the less dense it is. The warm, humid air is less dense than cold, dry air. So here we have warm air down here, cold air here, and so the front is the boundary between the two. This is just the front. But if for some reason or another a low pressure anomaly develops, then air begins to flow to that low pressure and begins to rotate. In this case, it's rotating clockwise. Okay, so as it rotates, the front separates. This becomes a warm front and this becomes a cold front. So warm front has the semicircles and the cold front has the triangles. Why is this a warm front? Because what we name a front based off of what air is following it. So warm air is coming behind this warm front and cold air is coming behind this cold front. But if we look at a cross section across these fronts from A to B, look at it down here, see the cold air is dense. So once it's staying at the surface, so the warm, humid air, it rises up gradually over the cold, dense air. And so as it rises gradually, it gradually cools and it gradually hits the lifting condensation altitude, and the water vapor begins to gradually precipitate out and fall as rain. So you have this widespread precipitation, nothing's concentrated. But as this cold front moves in, it pushes the warm, humid air out of the way and pushes it almost straight up. We have this warm, humid air rising straight up, and so all that water vapor is taken up into the air and it condenses out because the air adiabatically cools. And it releases that heat, the latent heat of vaporization into the atmosphere. What that does is it makes the air up here warmer. Because it's warmer, it makes it more buoyant, makes it want to rise with more vigor. Because this air wants to rise with more vigor, it pulls air in with more vigor, so it increases the wind speed. And with the wind speed increase, that means there's a faster rate at which warm, humid air is going to flow up here. And that humid air, the water vapor, the latent heat of vaporization, is the source of energy that's fueling this storm, because more water vapor goes up. And then when that more water vapor goes up, it cools, that water vapor condenses, releasing more heat to the atmosphere, increasing its temperature more, making it rise even more, increasing the wind speed, pulling even more warm, humid air in. That's these storms, they escalate, they intensify. Now, and we'll talk more about storms when we talk about extreme weather. So the jet stream, which you may have heard of, is this relatively narrow bands of high velocity air, about 200 kilometers per hour, that flows from west to east at high altitude. Now, why this happens is because as this warm air rises and this cold air rises, the pressure in the warm air decreases more slowly as you go up through the atmosphere than it does the cold air. The pressure decreases more quickly. So what happens is a higher altitude, there's a higher pressure down here, and there's a lower pressure up here. So as a result, air flows from low to high pressure. Low to high pressure. But in the northern hemisphere, the Coriolis effect deflects the path to the right. And so you have this air flowing around the Earth at high altitude. Right? And so that's the jet stream. And jet stream usually acts as a boundary between this cold polar air and the warmer air down here. And storms usually, so the fronts form along the jet stream. And then, so the fronts form and cyclones form along that front. And then usually the storm, the cyclone, tracks along the jet stream. And we'll talk more about that in future lectures as well. So looking at observed circulation in the atmosphere, there is significant variation of air pressure and wind patterns by hemisphere and season. So for example, seasonal changes are not so great in the southern hemisphere because there's not as much of a difference between surfaces. What that means is there's much less landmass in the southern hemisphere. You only have South America, the southern part of Africa, and Australia and Antarctica. We have much less landmass. It's mostly water, so you have much less of a difference between specific heats of surfaces. Where the northern hemisphere, there's much more dramatic change with seasons because you have more evenly distributed land and water surfaces. So winter has strong high pressure air masses of cold air over continents, and summer has thermal lows over continents, which creates high pressure zones over the Pacific and the Bermudas. Which is the oceans to the east and west of North America. So then the energy absorbed by the sun sets the atmosphere in motion, also sends the ocean in motion. So in the ocean, there's surface and near surface waters. They participate in currents. And these currents are waters that absorb and store huge amounts of solar energy. And they transport that energy from low latitudes, near the tropics, to higher latitudes, and poles. And then there's also some solar heat that's transferred deeper into the ocean by tides and winds. The surface in the deep ocean circulation transfers heat throughout the ocean. That affects global climate because as heat is transferred to deep parts of the ocean, that heat is essentially removed from the atmosphere. And so that process stops, then actually some heat will stop being sequestered into the deep parts of the ocean and the climate could warm up faster. If that process accelerates, the more heat can be taken down to the deep ocean and it can cause a cooling or a slowing of warming of the climate. So surface circulation is pretty much driven by winds. So we know that we know why the wind blows because of the thermal imbalance between the tropics and the poles. And so what that is the top layer of water is being drugged by the friction of the air moving over it. So it begins to move. And that top layer, it drags the layer beneath it, and that layer drags the layer beneath it, and so on, down to about a depth of 100 meters. And so you have water at the surface moving because it's being driven by the wind. The wind-driven flow directions are modified by the Coriolis effect and their deflection off a continent. So as the wind's blowing in a certain direction and the water begins to move in that direction, its path is then deflected to the right by the Coriolis effect. And these currents, they carry heat from low latitudes toward the poles. And you can see those surface circulations. So you see this is one circulation where it's taking warm water from the tropical Atlantic to higher latitudes and then back down. There's another surface circuit, another one here, and one more here. Right, so these are driven by wind. So the trade winds blowing this way, they pull the water east to west. And then the westerlies up here, they pull the water west to east. The water west to east. So the water, and then whenever the water comes in contact with the continent, it's forced to turn. Right? In deep ocean circulation, looking at the ocean is layered by density, which as you go down, the density increasing. And so this density increases by lower temperature. So the deeper you go, the cooler the water is. So it's denser. And it increases all salt content. And so if you change the temperature and the salinity of water, you change the density. And then, we know that dense fluids, they sink, and less dense fluids rise. So in the ocean, there's this very slow overturning of the ocean. So water sinking from the surface down to large depths. And as a result, water from depth rising to the surface. This is called the thermohaline circulation, because it's driven by differences in temperature. This thermo and haline means salt. So this is an overturning circulation. It's very slow. It takes about 100 years to make one full cycle. What happens at high latitudes near the poles, the water is much cooler. Near the Arctic and Antarctic, fresh water is entering the ocean from, whenever the water freezes to form sea ice, the salt is left behind in the water, so the water becomes saltier. So the water at high latitude, is cooler and saltier, which makes it denser. And so it causes that water to sink. And then water rises from the depths near the equators. So the densest ocean water forms in the Atlantic Ocean and the Southern Ocean near the poles, or at least around Antarctica and the Southern Pole, and it sinks to the bottom. And this thermohaline circulation, as I said, is very important because whenever that water sinks at high latitude, it's taking heat down with it. And that's helping bury some of the heat in our atmosphere. And so the fear is if eventually the water at the surface becomes too warm that it can't sink anymore, then the ocean will completely stratify, which means completely layer and stop turning over, and it'll stop taking heat down with it. And so it'll increase the speed at which our climate is warming. And there's also other implications of this thermohaline circulation shutting down that are thought to have been the cause of mass extinctions actually in Earth's past. But so it's an important circulation even though it's slow. So that's it for our external energy lecture. I'm sorry this part was much shorter, but I just couldn't fit in the time I had with the first part.